E300 Linear Circuit Analysis 2, Module 3, Video 3, First Order Circuits. In this video, we'll review what we did previously. We'll look at a first order low pass circuit, and a first order high pass circuit, and then a first order circuit that has shelving behavior. And then we'll summarize what we've done and look at future videos. So to review, we've been talking about the frequency response, which is we write as h of j omega. That's where s has been replaced by j omega. And we plot that versus omega. We call that the frequency response, and we plot the magnitude of it. We plot the angle of that, and then we do that versus omega. And we also, here's our familiar RC circuit, this time with the resistance of 10 k ohms and a capacitance of 1 microfarad. And we've seen this frequency response before when we plot it on a linear frequency scale. Here it is up to 2,000 radians a second. We see that it goes through the value of 1 over root 2 at the corner of 100. So this is 100 over s plus 100. And then at 1,000, it's down to 0.1. The gain is down to 0.1, and it keeps going down. The angle decreases from 0 to minus 45 degrees at the corner at the frequency 100, and then it decreases asymptotically to minus 90 degrees. We also saw Bode plots, which is a way of looking at the gain in decibels, 20 log base 10 of mag hj omega, and you plot that versus frequency on a log scale. For the magnitude plot, the angle plot, you just do the degrees versus frequency on a log scale. So for that same circuit, with the h of s equals 100 over s plus 100, here you see it's flat below 100 radians a second. It's largely approximated by a gain of 0 dB, and it rolls off. We say it rolls off. It decreases at a slope of minus 20 dB per decade when it's higher than the point omega equals 100. The angle curve we see is about 0, below a factor of 10 or so, below 100. And then you can see the asymptotic behavior down to minus 90 degrees there for high frequencies. So we want to use these Bode plots. We want to look at this in more detail in this video. And we also want to look at some other behavior of the circuit. And we're going to try and use the properties, talk about this in terms of the circuit, not just in terms of the mathematics of the frequency response. So let's look at the low-pass circuit. This is really what we just looked at. Let's call it a low-pass circuit. Here's our RC circuit. We know we can write this as alpha over s plus alpha. And then if we replace s by j omega, we get alpha over j omega plus alpha. And then factor out the alpha from numerator and denominator, we get 1 over 1 plus j omega over alpha. So that you can see why things matter about whether omega is equal to, bigger than, less than alpha, because of the relative sizes of the real and imaginary part, the denominator there. But what's going on in the circuit? Well, for low frequencies, when omega is very much less than alpha, or you can say when omega is approximately equal to 0, that's when the capacitor, right? The capacitor impedance is 1 over j omega, 1 over j omega c. And when omega is small, 1 over j omega c is big. And so it's big, and so no current flows through, or little current flows through the capacitor. And if little current flows through the capacitor, then you can't get much voltage across there. Then all the voltage has to be across there. Little voltage is showing up across the resistor. All the voltage is showing up across the capacitor. We know even, for the most extreme low frequencies, omega equals 0, and the capacitor acts like an open circuit, and then V2 is just equal to V1. So the magnitude of h of j omega is approximately equal to 1, and the angle of h of j omega is approximately equal to 0. We call this the pass band of the circuit. The output is about equal to the input. On the other hand, when we go to high frequencies and let omega equal big, now the imaginary part down here is big, and that's going to make, you can see the denominator is going to be bigger than 1, and so that'll make things roll off in the high frequency behavior. Physically, for high frequencies, 1 over j omega c gets small. It gets small. This acts more like a short, and if it's acting like a short, then there can't be much voltage across it. And that means more currents flowing here. That means more currents flowing through the resistor, and so more of the voltage can drop across the resistor. So for omega very much greater than alpha, or omega going to infinity, the capacitor conducts more. The voltage drops across the resistor. The magnitude of h of j omega looks like minus j alpha over omega. Again, that's when this term, when the j omega over alpha dominates everything, then you just get that flipped into the numerator, so you get minus j alpha over omega. It acts like 1 over omega, and the angle of h of j omega is approximately minus 90 degrees. We call that the stop band of the circuit. And then at the frequency omega equals alpha, that's when 1 over omega c is r. That is because that's when omega rc is equal to 1. And that's the case, then you have 1 over 1 plus j in the frequency response. So the magnitude is 1 over root 2, and the angle is minus 45 degrees. We call that the corner frequency, or the half power frequency. Remember, if the magnitude is scaled by 1 over root 2, then the magnitude squared, which is going to be the power, is going to be a half. So when we do our low-pass circuit, we have a pass band, and we're going to take that. I mean, the pass band, you can define it arbitrarily, but we're going to take just frequencies less than the corner frequency. So as long as half the power or more of the incoming signal gets through, we'll say that's passing the signal. The stop band is going to be frequency higher than the corner frequency, which is where it attenuates more than half the power. And then we call this a low-pass circuit because it passes the low frequencies. The low frequency inputs show up with little attenuation or phase shift at the output, whereas the high frequency signals get attenuated with a phase shift. And we look at this on the Bode plot. For the gain, let's look at the upper panel here. We see the passband gain is 0 dB. That's an ordinary gain of 1. 20 log base 10 of 1 is 0. At the corner frequency, which we're plotting, this is versus omega over alpha. So this is normalized by the corner frequency alpha. So at the corner frequency, we get a gain of minus 3 dB. That is, it's attenuated by 3 dB. It's got a factor of 1 over root 2 in the ordinary gain. That's the half power point. In the stop band, the gain just gets smaller and smaller and smaller as frequency gets higher, and it just keeps going smaller and smaller, and it does that at a rate of what we call 20 dB per decade. You can see that the gain decreases by a factor of 10. So it goes from the ordinary gain here would be 0.1, the ordinary gain at minus 40 dB would be 0.01, and then down to minus 60 dB where it would be 0.001. So for every increase in frequency by a factor of 10, the gain goes down by a factor of 10 or by 20 dB. This high frequency asymptote, which has a slope of minus 20 dB per decade, intersects the low frequency asymptote, which has a gain of 0 dB, at the corner frequency. And you can see the biggest deviation there is at the corner frequency, which is only 3 dB. So this is a pretty good approximation to the behavior of the low-pass circuit. In the angle curve, we're going to look at the lower panel here. Now again, we're plotting versus frequency normalized by alpha, the corner frequency. So 1 is the corner frequency. This 10, a factor, this is a decade below the corner frequency, a decade above the corner frequency, etc. The angle, when you're well below, when you're more than 1 decade below the corner frequency, the angle is about 0. At the corner frequency, the angle is minus 45 degrees. And when you're above 1 decade above the corner frequency, then the angle is pretty well approximated by minus 90 degrees. And again, if you put an asymptote, if you take these, the low frequency asymptote up to 1 decade below the corner frequency, the high frequency asymptote 1 decade above the corner frequency, and you connect those with a straight line, it goes through minus 45 degrees at the corner frequency, and it has an angle that's 6 degrees. 6 degrees is the biggest error there. And again, that happens at that point where the asymptotes meet. So we have a low frequency asymptote, a connecting asymptote, and a high frequency asymptote. And these straight line approximations are within 6 degrees of the actual curve over the entire range of the circuit behavior. Let's look at a high-pass circuit. This is just looking at the output across the resistor. So we have the same kind of factors. When omega is small, when the frequency is small, there's no current through the capacitor. And if there's no current through the capacitor, then because it's acting like an open, then there can't be any voltage across the resistor. We can look down here at the mathematical formula for this, and you can see that for low frequencies, this term is going to go in the denominator. The j omega over alpha term is going to be dominated by 1, and so we just get j omega over alpha. So it's actually going to increase proportionally to alpha. The size of the gain is going to increase proportional to alpha, to omega in the low frequency regime, and you're going to have an angle of 90 degrees associated with the imaginary number j there. For very high frequencies, okay, now the capacitor is acting like a short, so it's letting current flow. All the voltage is dropping across the resistor. There's no voltage dropping across the capacitor, and so the gain is approximately equal to 1. You see that in the mathematics down here. When the omega gets big, then the J dominates, the J omega over alpha dominates the 1, and the ratio of the J omega over alpha to J omega over alpha is just 1. And as before, when omega equals alpha and the 1 over omega c is equal to r, then you're at your half power point, and the frequency response is J over 1 plus J, so you get a 90-degree term from the numerator, you get a 45-degree term from the denominator, and 90 minus 45 is going to give you a 45-degree angle and a 1 over root 2 magnitude there. This is a high-pass circuit. It's got constant gain for high frequencies, and it attenuates less than 1, because this is when omega's less than, this would really say J omega over alpha. When omega is less than alpha, then omega over alpha is going to be less than 1. So this should have a J omega over alpha there. And let's look at this as the gain term. Let's look at the upper panel of the Bode plot here. In the passband, for frequencies bigger than the corner frequency, then the gain is 0 dB approximately. So the passband for the high-pass circuit is bigger than the corner frequency. Omega is bigger than the corner frequency. At the corner frequency, the gain is down by 3 dB, and below the corner frequency, the gain is increasing with increasing omega by 20 dB per decade up until it reaches the corner frequency. And this just keeps, again, it's got a, in dB at 0, it's got a gain of 0, so it's minus infinity. So this is a straight line for every, if we're decreasing the frequency from 10 below the corner frequency to 100 below the corner frequency to 1,000 below the corner frequency. At 1,000, a factor of 1,000, that is the corner frequency divided by 1,000, then you're going to have an attenuation of 60 dB there. So the high frequency asymptote, which has a slope of plus 20 dB here in the high pass filter, intercepts the high frequency asymptote. The low frequency asymptote intersects the high frequency asymptote at the corner frequency. We can look at the angle curve, the lower panel here. So 1 decade above the corner frequency, the angle is about 0. At the corner frequency, the angle is plus 45 degrees. And when you're more than 1 decade below the corner frequency, now you've got an angle of 90 degrees. And these connect again by an asymptote that goes from 90 degrees through 45 degrees down to 0 degrees over the 2 decades surrounding the corner frequency. And again, the maximum error is 6 degrees. Okay, let's look at a slightly different kind of circuit. This one has what you call shelving behavior or frequency shaping behavior. The first two, the low pass and the high pass, are called frequency selective filters because they select a band of filters, a band of frequencies to pass, and then the rest of the stuff they attenuate. This is a shelving circuit which is going to have different gains at different frequency bands. So I'm not going to go through the derivation of the transfer function here. You can go through that. But we can show that its h of s is 0.1 times s plus 10,000 over s plus 100. So this circuit has a 0, you can see, okay, let's go back here. When we have a low frequencies, the capacitor acts like an open, so the voltage, all the input shows up across the capacitor in series with the resistor. And you have this factor of 10, I think these are backwards. This ought to be, the 100 k ohm ought to be in the this branch down to the lower terminal here, and the 900 k ohm, because this is supposed to be a gain of 10. Not a gain of 10 over 9, not a gain of 10 ninths. It's supposed to be a gain of 10. So this should be a 900 k ohms in this branch from the minus to the output, and this should be 100 k ohms from the minus to the bottom terminal of the circuit. Anyway, when this is open, then you're just going to have all the voltage is going to show up across the 10 k ohm resistor. There's no current through the circuit, and so you to get the gain of 10 that ought to be coming from the op amp if it had the resistors in the right place. So that's a 20 dB gain at low frequencies. For high frequencies, now this is acting like a short, and we have the voltage divider between the 990 k ohm and the 10 k ohm. So 1/10 of the voltage shows up across the 10 k ohm resistor in that case, and in series with the capacitor. And so that's a gain of 0.1, you get minus 20 dB. The circuit has a pole at minus 100 and a 0 at minus 10,000. So let's see what the Bode plot for this looks like. The upper panel is the magnitude, lower panel is the angle. This is the argument here is actually in the radians per second. That's not normalized by anything because you have both a pole and a 0 here. So the passband with 20 dB gain is below 100 radians a second. That's where the pole was at 100 radians per second. And you can see if you just looked at the left part of the circuit, it looks like a low pass filter with the 20 dB gain and then rolling off at 20 dB per decade. But then you get up to the 0 frequency at 10,000 radians a second, and it flattens out. So in this case, it goes from 20 dB gain through 0 dB gain at 1,000 to minus 20 dB gain, or 20 dB of attenuation, above 10,000 radians a second. There's a transition between, and so this is a frequency shaping circuit that it accentuates, boosts the low frequencies, and it attenuates the high frequencies, but it doesn't put any frequency selectivity above them once it gets above, say, a 10,000 radians a second. The angle curve, you can see it's trying to approximate, again, the behavior of the pole, and then you see something that looks sort of like the behavior of the 0 as the angle goes back up by 90 degrees around the 0 frequency of, or around the corner frequency associated with the 0 at 10,000 radians a second. We'll talk more about this when we talk about Bode's method for drawing frequency responses by hand, but for now, and also when we talk about the vector interpretation of pole 0 diagram, of frequency responses in terms of the pole 0 diagrams, and that'll be coming up next week. So again, this is called a frequency shaping circuit. So to summarize, we've had shown that first order circuits can have frequency selective behavior, low pass or high pass. They can have frequency shaping behavior. And if there had been another capacitor here in this branch here, we could have gotten the gain at the high end to be higher, the high frequency end to be higher than the gain at the low frequency end. So we can have frequency selective shaping behavior where we have a boost for higher frequencies relative to the low frequencies too. This is the kind of filter that would be in your equalizer, for an audio equalizer, where you want to boost the low frequencies, attenuate different frequency bands. So back to this. Back to summarize, we've got frequency selective behavior, we've got frequency shaping behavior. We can approximate the Bode plot with straight lines, and we'll do more of that in the future. For the low pass behavior, the gain decreases at minus 20 dB per decade, and for high pass behavior, the gain increases at 20 dB per decade. And these are both in the stop band. And at the corner, the gain is minus 3 dB relative to the passband gain. So what we're going to do next is do the same kind of thinking for the RLC circuit, both in overdamped situations and in underdamped situations. So this has been Module 3, Video 3, First Order Circuits. This is EE300 Linear Circuit Analysis 2.